So now I'm going to program for fixed point iteration. And the function under question is g of x, and it is 1 by 2 10 minus x cube. Okay. 1 by 2 and 10 minus x cube. Okay. So I have to define the function g of x, and it should return a value g is equal to 1 divided by 2 times numpy square root of 10 minus x cube. So, okay, I write x cube in this form, and then it should return the value of g. Okay. Now, let's see this problem for few iterations. So I define number of iterations, say 10, and I have to start with an initial guess. Since we know from the problem, the interval is AB, 1 to 2. We are looking for a fixed point here. So the algorithm begins. So I write for I in range number of iterations. So 10 iterations will be performed. So I have to have one x specified. Okay. So x old is equal to, say, 1.5. And then the new value of x will be equal to g of x old. Just to show you the working of algorithm, I define y1 is equal to old, g of x old, and then we set this value on the straight line. We set it equal to the value on straight line, and then x new value is generated as y2. Right. So that is just a matter of writing. I can directly write. This is just equivalent to writing x new equal to g of x old, and that's it. So just to show you the process, the way we trace that one on the graph, we see the value on the function, on the curve. This is like looking for value on curve, right? And this is like intercept it on straight line, and then get the abscissa, new abscissa, get new abscissa value, right? And then the next step is to calculate the error. So error is equal to numpy absolute of x new minus x old. Since we are looking for it to converge that one, so it is, well, it's a kind of practice to write this one as x old minus x new with reference to the more closer value. And then I print some values. So printing, and I will print the values of number of the iteration value, x new value, and the error value, and they require their respective formats. So I define 5 digits or 5i for integer, then %10.5 f for x new, and 10.5 F for error. So this is going to perform 10 iterations, number of iterations 10. So we can see whether the algorithm is working or not. And later on, if you see that it is converging, then you can increase the number of iterations. Okay. So for these many number of iterations, so well, nothing has happened. For y1 x new equal to y2, then x new. Oh, we didn't change the value. Sorry, the new value was computed, so this should be just the. Okay. Let me see. Okay, this is the x new value, and then we have to update. Then we have to update as x old is equal to x new, right? We didn't updated this one for the next iteration. So now, yes, it has worked. 1.36. You can see from the number of iterations. So the error is reducing, right? Error is reducing. So this is the algorithm for the fixed point iteration. So if I would like to show you the smaller version, so it just required one line, x new is equal to g of x old, and then the error calculation. So just one line. From an old value, get the new value, and in between, it is going to find the value at the same ordinate on straight line, and then there is the update. So yes, it's very nice. If you increase the number of iterations to 20, for instance, so then okay, so the convergence is so fine that the provided format with 5 decimal places is inadequate to show you the results. So the formatting requires the more precision. So this is the demonstration on fixed point iteration. I stop at this point.